Now, so we'll be looking at zero knowledge proofs. And so first of all, I'll define what that is. And I've said here that zero knowledge, which we also abbreviate as ZK proofs, is a concept in cryptography that allows one party to prove to another party that a statement is true without revealing any additional information beyond the validity of the statement. Now, so what I mean here is that, okay, we have two persons here. We have the prover and the verifier. So the prover knows something but does not want to reveal what that thing is. And the verifier wants to verify whether it's true the prover knows what he claims to know. So then they agree on a way of going through that proving, the algorithm, how to prove it. I can begin with an example. For instance, let's say the two people are walking along the way. Let me say person A, let me say Alex, for instance, is walking with let me see who is here, with Wanjiru. So they are along the way walking. Then Wanjiru claims that when she looks at any tree, she can immediately say the number of leaves on that tree. She can say the number of leaves on a tree by just looking at it instantly. So Wanjiru claims to have that ability. Then Alex will wish to see whether Wanjiru can really do that. And so while they're walking, Alex sees a tree, then asks Wanjiru, are you able to tell how many leaves are on this tree? Now, Wanjiru does not want to reveal how many leaves are there, but she claims she has that ability. So Alex is aware that Wanjiru does not want to say how many leaves are there. But now Alex wants to know whether it's true. Wanjiru has that ability. So while Wanjiru is facing aside, Alex plucks a few leaves from that tree. Let me say 10 leaves. Alex plucks 10 leaves from that tree. Then ask Wanjiru. Wanjiru did not say how many leaves Alex plucked. But Wanjiru has the ability to tell how many leaves are on that tree. So she had looked at them, and then she had seen how many they are. So Alex has plucked 10 leaves without Wanjiru seeing. And then he asks Wanjiru, how many leaves have I plucked from this? So now they have now started the process of verifying. Alex wants to verify. Alex is the verifier, and Wanjiru is the prover. The prover is the person who has the idea, that information, but does not want to reveal what it is. So Alex has asked Wanjiru, how many leaves have I plucked from this tree? Then Wanjiru looks at the tree again, then tells Alex, you've plucked 10 leaves from the tree. You see, Wanjiru did not say how many leaves Alex said, but Wanjiru knows how many leaves are on that tree. So by looking at the tree, she can see that the tree now has 10 leaves less. So she tells Alex, you plucked 10 leaves. So Alex again waits when Wanjiru again is facing aside, again he plucks other leaves, like let me say 5. Then ask Wanjiru, how many leaves have I plucked this time around? So Wanjiru looks at the tree again, then tells Alex, you plucked 5 leaves from the tree. So you see what Wanjiru is doing, she's trying to prove that she knows how many leaves that a tree has. But she doesn't want to tell Alex how many leaves are there on the tree. But using some ways, she's able to show Alex that indeed she knows how many leaves are there. Because nobody can tell Alex, for instance, that you plucked 10 leaves from that tree if that person did not know how many leaves were there originally. Because this person is just looking at the tree, then telling you, now this tree is less 10 leaves. It means this person knows how many leaves are on that tree, total number of leaves. But it doesn't want to tell it doesn't want to tell Alex, she doesn't want to tell Alex how many leaves are there. So that is the secret. She doesn't want Alex to know, but in some way, she will convince Alex that indeed she knows how many leaves are there. So that is the concept of zero knowledge. Zero knowledge, you try to prove to somebody that you have this kind of information, but you do not want to reveal the information to this person. So this, you then agree in some way, you agree in a way that you can convince this person that indeed you have this information. So that is the zero knowledge. So that is what I had written here. It said, in other words, the prover convinces the verifier that they know a piece of information without revealing what that information is. So you see, in this example of the leaves, Alex has listened to Wanjiru for quite some time, but at the end of the day, the only information Alex goes away with is that Wanjiru has the ability to tell how many leaves are on a tree by just looking at the tree at once. It doesn't go out with information of how many leaves are on that tree. So he will not get this information. Wanjiru has decided to hide this information. This is secret information. So she doesn't want Alex to know how many leaves are here, how many leaves are there. But she has convinced Alex, because Alex is now aware that Wanjiru knows the number of leaves, because any intruder coming who doesn't know the number of leaves cannot tell how many you plucked from that tree, because doesn't know, of course, how many were originally on that tree. Now, so the verifier and the prover, they have to agree on a way of how to verify, to verify that this prover has the information. But the prover in the process has always to ensure that does not give more information than is required to the verifier. So you avoid giving more information. You only wait. If you ask this question, you reply just that question, but you ensure that the question does not lead to the information you're trying to hide. Now, so I'd given another example here, another example of zero knowledge. For instance, you and I agree on a puzzle, the Sudoku puzzle. Now, so in this example, it's you who has told me that you know the solution to the Sudoku puzzle. You know the solution. Now, I want to verify whether indeed you know, but you do not want me to know what the solution is. So you do not want me to know what the solution is, but you've told me you know the solution. Now, I just want to know whether actually you know that solution. I want to verify. So I challenge you. I take some row or a column from that Sudoku grid, and then I ask you to prove whether you know the numbers of that I've taken, the numbers of that row or the column. Now, you now want to prove. For you to prove, maybe you do some steps, which of course I should be knowing those steps. So you do those steps that will convince me that you know the numbers I took away from the row or from the column. So you just do a few steps that will want to convince me. So after you try to convince me, I'll try to verify. So the verifier must always verify after the prover has made his statement. So I check the steps that we performed and see whether they are valid. If they are valid, then I'll know that you have that information. I know that you know how to, the solution to that Sudoku puzzle. Now, why do we study zero knowledge? And I've said that zero knowledge proofs have numerous applications in cryptography. And some of the applications are this: authentication of protocols, digital currencies, like the Zcash. They use zero knowledge, and we shall see that which one they use. And we are also have, there are so many, even Bitcoin and so on, which use zero knowledge. And so zero knowledge, they're using it. You are giving your information, for instance, and it's supposed to be kept a secret. But you don't give a lot of information. That is, you only want to prove that you have this information and so on. Now, there are particularly zero knowledge proofs are particularly valuable in scenarios where privacy and confidentiality are important. So the parties will be proving statements without revealing sensitive information. That is what we've already seen, that is the essence of zero knowledge. You want to prove that you have this information, but you avoid giving some information. Now, so just to help understand the concept of zero knowledge, I want to use some mathematics. And the one I want to use the concept of the square root problem. And the algorithm is here. So the algorithm, we have this person called Cyprian selects two prime numbers and then publishes n. So Cyprian collects selected two prime numbers, then it gets their product n, then makes it public. He also selects a secret value x, and this x must be relatively prime to n. In other words, the GCD of x and n should be 1. But he will not publish x. X is the secret. What he'll publish is x squared. So first of all, he chose two prime numbers, multiplied them, and got the product n. This n he makes public. Then he chooses the secret. This secret value x must be relatively prime to n. And then what you publish is x squared mod n. Now, Alex wants to confirm if Cyprian knows x. Remember, it's me, it's Cyprian who chose this x. So he knows what x is. Alex wants to prove whether indeed Cyprian knows. But Cyprian does not want to reveal the x. Does not want to reveal the x. We are using zero knowledge proof. So you don't want to reveal the x. You reveal n. You reveal x squared. So Alex has n. Alex has x squared. So of course, when he'll be verifying, when we begin proving, when Cyprian begins proving, Alex will be verifying with x square and n. That is the verification process. Now, so they agree that let us prove. They agree that Cyprian should prove, and Cyprian to prove follows the following steps. The first step that Cyprian does, he wants to just to show that he knows what x is, but it doesn't want Alex to know what x is. Remember, x square has been published, and n has been published. So for Cyprian to prove that he knows x, the first thing he'll do, chooses another number, mod n, and that number must be relatively prime to n, relatively prime to n. After choosing that number, Cyprian gets its inverse, gets the inverse of this number. So he has chosen it. This number, he has not revealed it. He just is preparing himself to prove, because he has been asked to prove whether he knows what x is. So he chooses another number, which is relatively prime to n. And that number is not x, just another number. Then gets its inverse. Since he has x, since he knows what x is, he multiplies the inverse of n, the inverse of this u1, multiplies it by x. So it takes this inverse and multiplies by x. And we know how to do this. I'll be showing an example. We know how to get inverses using the extended Euclid's algorithm. I'll be showing an example. Now, so this product gives another number, mod n, and this number is u2. So he chose u1, which is relatively prime to n. Then got its inverse. Then multiplies this inverse by x to give you another number, u2. Now, when you take this u1 and u2 and multiply, you'll get x. But Alex does not know. Alex does not know this. He has not been told. So Cyprian has just chosen this number, then multiplied by x, because he knows what x is. He just wants to prove he knows x. He just wants to prove that he knows x, but he doesn't want to tell Alex what it is. What it is. Now, so chooses this u1, gets it in its inverse, multiplies by x, and you get u2. Now he goes to the next step. What's the next step? He gets the square of u1, call it x1. Then he finds the square of u2 and calls it x2. He sends to Alex x1 and x2. That's what he sends to Alex. Remember, let me remind you what Cyprian is doing. He's trying to conceal this x so that Alex does not know it. And he's just using it. He just wants to conceal it so that look at what he has done. He chose u1, got its inverse, multiplied by x, and that gives you u2. And he knows that this u1 and u2 is supposed to give you x, but he is not telling this, is not giving u1 and u2 to Alex, because if he gives u1 and u2 to Alex, Alex will be able to get x. So what he does is squares the u1 and squares the u2 and sends a u1, square of u1 equals it x1, and the square of u2 equals it x2. He sends this x1 and x2 to Alex. Alex tries the product of these two. And when he does the product of these two, it gives him x squared. And you know, he had been given x squared before. He had been given x squared before. Now, so Alex wants to verify. Wants to verify whether Cyprian knows what he has done. Alex asked Cyprian, give me the square root of x1, or give me the square root of x2. And since Cyprian knows what x1 is, he knows what x1 is. He took x1, and this x1 was what? X1 was the square of u1. So he knows that the square root of x1 is just the square root of this, which is u1. So it's very easy for Cyprian to give that information. And he also knows the square root of x2, because x2 was the square of u2. So if he is asked about the square root of x2, just guess the square root of u2, which is u2. The square root of this, which is u2. So Cyprian sends Alex what Alex has asked for. Now, so Alex now confirms. Alex looks at what he has been sent as the square root of x1. Then he squares it. Squares what he has been sent. And compares it with the x1 he had been sent. You see, he had been sent x1. So he squares this, what he has been sent again, and then compares with what he had been sent originally. Now, if he asks for the square root of x2 and is sent by Cyprian, again, for him to verify, he squares it and compares with what he has. Now, why is this square root problem important here? Because, you know, getting the square root mod n is not an easy thing. It's a very difficult problem. It's a very difficult problem. Anybody who can get, you see, if you're given x square mod n, it's not possible for you to get its square root and know what x is. It's not possible. It's a very difficult problem. It's not possible. For instance, if I was just to give you 2 mod n, let me say even mod 5, and ask you for the square root, is not a very easy thing. It's a very difficult thing. Getting the square root of these 2 is not a very easy thing. And in fact, it becomes very complicated if n is a huge number. If n is a huge number, it becomes very hard. So n was made public, x squared was made public, but the people who have it, they cannot get the square root. They cannot get to know what x is. It's only the person who chose. In this case, it was Cyprian. So he's the only person who knows what x is. So then this is a secret to him. So then Alex wants him to prove that he knows x. And he goes through these steps. He goes through these steps. So if there was an intruder listening to the conversation the intruder has is n. The intruder knows what n is. The intruder knows what x squared is. The intruder does not know what x is. So the intruder coming in and trying to pretend to be Cyprian may answer 1 or 2 questions correct. If Alex was to pose to him, he may answer 1 question correct, but a half of the questions will be answered wrongly by the intruder. A half of the questions will be answered wrongly because the intruder does not know what x is. And I'll show an example why the intruder comes in and tries to impersonate the person who has the secret information. And then when the intruder impersonates this person and tries to convince Alex that is now the Cyprian, Alex is able to tell that this is not, this is an intruder. He's able to tell. Because you just ask one question, the intruder is able to, but through guesswork, he may answer one or two questions correct, but other questions will not be answered correctly because it does not have the information. Now, I just want to go through again this algorithm, and then I show one example of how this algorithm is used to conceal some information. In this algorithm, I've used the square root, and I've already told you that getting a square root mod n is not easy. It's a very hard problem, especially when n is huge. When n is huge, it becomes even more difficult. So Cyprian has published n. He has also published x square mod n. But this is his secret. This is the information he will not allow anybody to know. Now, Alex wants to know whether this Cyprian or really knows this x, whether he knows what x is. And they agree that Cyprian is going to prove that he knows x. So Cyprian now begins to prove. He selects a number u1 mod n, which is relatively prime to n, then gets its inverse, multiplies this inverse by x because he knows what x is. He's the only one who knows, multiplies and then gets u2. And then it squares u1, call it x1, and then it squares u2, call it x2. He sends Alex x1 and x2. When Alex multiplies these two, he discovers they're giving him x squared. These two, on multiplying, he discovers they're giving him x squared. So you see the problem to Alex was getting the square root. That was his problem. Now he wants to know whether Cyprian can get the square root of x1 and the square root of x2. Because if Cyprian can get the square root of x1 and x2, it means he can get the square root of x squared. He asked Cyprian, give me the square root of x1. And Cyprian comfortably gives that information. He may again ask, give me the square root of x2. And Cyprian comfortably provides. So when Alex asks for the square root of x1 and is given, he squares that square root. He wants to confirm whether indeed this prover has given the square root. Because he knows getting the square root is not easy. Mod n. He knows getting the square root of x1 is not easy. So he asks, give me the square root. So, and the square root is provided. So he tries to verify, is it really what I've been given? Is it really the square root? To verify this, you square it. So when he squares, he finds, in fact, it gives him x1. Then he asks, now give me the square root of x2. And again, is given. He squares it. And if he finds that when he squares it, it gives him x2. He's convinced. He's convinced this guy can get the square root. Only the person who can get the square root is the one who has the number, not any intruder. So let me show an example. Now, just an example here. Let n be this number and x squared be that. Now, suppose Cyprian claims to know x, the square root of this. but is unwilling to disclose. Alex challenges him to prove he knows. You know, it's not easy to get this square root if you don't know x. It's not easy. So anybody who knows x is the only one who can get this square root. But in fact, the prover does not want to get the square root. Does not, because if he gets this square root, he'll have revealed the x. And you know this is zero knowledge. You don't need to reveal x. The verifier is supposed to go away knowing that you know x, but he should not go away with the knowledge of what x is. He should not go away with the knowledge of what x is. He should just go away with the knowledge that you know what x is. That is the only thing he's supposed to gain from you. Every other thing, he should not get it from you. Okay, so Alex has convinced me, has asked this Cyprian to verify he knows x. Cyprian has decided to choose a number u1 and gets its inverse. I think we know how to get the inverse of this. Let me just again show you how to get the inverse. We are doing this mod 814, just for the sake of those who may not know. He has chosen u1. He has chosen u1 as 317 mod. Our n was 12. No, our n was 14,863. Now, what is x? X is he knows x. He knows x as what? Okay, he has not revealed what x is, but he knows what x is. Let me just find out what x is. X, Cyprian knows x to be 583. He knows x to be 583. Now, let's now go to the process of proving that Cyprian knows. So Cyprian has this u1, gets the inverse mod 14,863. Of course, he's using the Euclid's algorithm. So he's first of all using Euclid's 14,863. How many times does 317 go there? There's some calculator. Okay, so I'm just using my calculator. 14. Let me admit this one first. 14,863. 317 goes there 46 times. Goes there 46 times. This is 3 what? 3. 17 was going there 46 times. What's the remainder? $281. Then $281 into 317. Divided by 281 goes there once. So 317 goes there once. 281 goes there once. And the remainder is 36. Then 281 divided by 36, 7 times. 7 times. And the remainder is what? The remainder is 29. Then 29 to 36 once. The remainder, no, it goes there, 21 goes there, 29 goes there once, and the remainder is 7. Then 7 29, 7 into 29, 4 times. And that will be 28. That'll give you 28. Eh? The remainder is 1. So this is the GCD. So when you reverse this, I'll not go through that. So when you reverse that, you'll get you'll get that inverse as 12, 9, and 800. 12, 800 is the inverse. So here I just use extended Euclidean algorithm. When you do that, you get the inverse of, it was 317, yeah? Mod, was mod what? Mod 14,863, mod 14,863. 14,863. Find this inverse to be, we had seen it to be what? The inverse is 12,800. 12,800. Now, so after getting this inverse of U1, after getting the inverse of U1 to be 12,800, you need to get U2. You need to get U2. And U2, you just get X. You must know what X is for you to get U2. That is now where the intruder, when the intruder was, if the intruder comes in, it'll be found. X is 583. 583. So CPAN knows X is 583. So multiplies this by 12,800 mod 14,863. What do you get? Now, if anybody has a calculator and you've gotten the answer, you just tell me. That is 583 times 12,800, then divide by 14,863. Because there are 502 times, 502 times, and the remainder is 1174. So this is our U2. Now, so we had U1, which is 317, and U2 is that. You don't send to Alex that, because if you send Alex 317 and this, he will know what X is. We still want to conceal X. Because when you multiply this two, they'll give you X. Let's just see. When you multiply 317 times 1174, if you multiply 317 times 1174, this is what you get. You get 372, 158. And we are doing it mod 14,863. So when you do this mod 14,863, it goes there 25 times. 25 times. And the remainder is X, which is 583. So we don't want to give him that. Want to conceal that information. So to conceal that information, once you get U1 and U2, square U1 and square U2. So you get X1. X1 is the square of U1. And what is U1? U1 is 317. 317 mod 14,863. 14,863. So let's just square that. 317 times 317 mod 14,863 goes there 6 times. 6 times. The remainder is 11,311. Now get X2 by squaring U2. By squaring U2, and U2 we had found it. We had found it to be 1174. And we are doing this mod 14,863. So let's just square that. 1174 times 1174, and then divide by 14,863, goes there 92 times. Goes there 92 times. And what is the remainder? The remainder is 10,880. So now you send to Alex X1 and X2. You send him X1 and X2. When you send him that, he wants to know whether it's the same as X squared. So he takes, Alex now takes X1 and multiplies by X2 mod 14,863. Just trying to see whether what we are sending is correct. So you remember I said that when the verifier does his verification, the prover is supposed to go through the steps and see whether they are valid. So Alex, when he receives this, he just verifies to see whether that is a valid step. So he takes X1, which is 11,311, and multiplies by 10,880. And you get that a big number, but now divided by 14,863. It goes there 8279 times. 8279 times. 8279 times, and the remainder is 12,903. He compares to see whether this is the same X squared that he was sent earlier. Wants to see whether the same as X squared, he goes back and checks that he was sent X squared. Where was that? X squared was 12,903. 12,903. And he has just received that. That is what he has gotten. Now he sees that this person, of course, he wants to confirm whether this person really knows what he's doing. Might just have chosen these values randomly. So now he asks this person, can you give me the square root of X1? Give me the square root of X1. So Cyprian has been challenged to give the square root of X1. What is X1? X1 is 11,311. The square root of that, because Alex knows that getting the square root mod 14,863 is not easy. But you see, Cyprian will not struggle because he's the one who squared to get this number. He just squared a number. So he just goes back to what he squared. What he squared was 317. He squared 317, and 317 is what gave him x1 on squaring. So when he's asked to get the square root of x1, he forwards to Alex 317. So Alex has to confirm whether 317 is the square root of 11, 311. So he squares also. Because he cannot get the square root of 11, 311. He cannot. Mod 14, he cannot. But Cyprian has produced it. So now he squares, Alex also will now square it. And on squaring it, he will see, indeed, it's giving him 11, 311. Then asked Cyprian another question. Now provide the square root of u2. Now the square root of x2. x2 is this. x2 is this. So getting the square root, Cyprian just goes back and sees what he squared. He squared 1174 and then gives to Alex. He sends Alex 1174. Alex is now convinced. By the end of that, Alex is convinced Cyprian knows what x is. Because he was able to give Alex x squared broken down. X squared broken down. Gave him x1 and x2. And then he has been able to get the square root of x1 and the square root of x2. And send it to Alex, the square root of x1 and x2. So Alex should be convinced. Anybody trying to impersonate Cyprian may not prove all of them, may not give the square root of x1. Or if he manages to give the square root of x1, then he will not manage to give the square root of x2. He can only give one of these two. Can only give one. And I'll show you by an example that the impersonator can only give a half of the proof, can only answer a half of the proof correctly. If he was brilliant enough, if he's bright and he's very good at impersonating, he can give only half of the proof correctly. But the remaining half he cannot. And that means at the end of the day, you can tell that this person is not the original person that we're supposed to be talking to. He's an impersonator. I'll show you an example again, another example, then show you how the impersonator comes in and fails. Another example, again, this time n is 7081 and x squared is provided mod n. Now the square root, the person who is proving this, the Cyprian claims to know what x is. He's claiming he knows. He's claiming he knows this square root. But he's unwilling to disclose to Alex what it is. As before, chooses any number. You see, it's not a must, you must choose this. You can choose another number. But what we said, this number that you choose should be relatively prime to n. That is the only condition. Should be relatively prime to n. You can even choose 3. Because I can see 3. Can 3 divide this number? 3 cannot divide this number. So you can even choose 3 to be u1, so long as it's relatively prime to n. But after choosing that 3, you get its inverse. You get its inverse. Using the Euclid's algorithm and the extended Euclid's algorithm, you get its inverse. Now this inverse, after getting it, since you know X, since it's you who knows, and Alex wants to prove whether you know it, multiply that X by 1980. So you know that maybe you knew X is this. From the start of the question, you know X is this, and this is what you want to prove that you know. So since you know it, multiply it by that inverse. And that product is supposed to give you U2. That product is supposed to give you U2. And of course, when you multiply, you are doing it mod 7081. Mod 7081. So get this product and then divide by 7081, get the remainder. This remainder is U2. Don't give U2 and U1 to Alex, because if you give him U2 and U1, he will get X. And you want to conceal it. You want X to remain secret. You don't want anybody to know. So what you do, after getting U1 and U2, square U1 and square U2. When you square U1, you get, call it X1, whatever you get, and you're doing it mod 7081. Mod 7081. So let's just do it a bit, just a bit. Let's just do a few calculations, a bit. If I show you how the intruder would have difficulty. So we are doing, you have chosen U1 as 211. So you've chosen U1. So your U1, you've chosen it to be 211. And the mod, your N is 7081. I think, let me see. Yes, 7081. And you know X. You know X is 301. You know that X is 301, but you don't want to reveal it. This U1 is 211. U1 here is 211. U1 is 211. Good. Now, you are now ready to prove to whoever wants to know whether you know X. So the first thing you do, get the inverse of U1. Get the inverse of U1. Get the inverse of U1 mod 7081. So in other words, we're getting the inverse of 211 mod 7081. Of course, we have various methods of finding the inverse, but we want to choose the Euclid's algorithm and the extended Euclid's algorithm. So using the Euclid's algorithm, you would want to ask yourself, how many times does 211 go into that? Just want to show a bit, and then we do the calculation, because I know you can complete. Now, so that is 7081, dividing it by 211, goes that 3 times. That 3 times. 211 goes that 3 times. What is the remainder? 118. What about 118 into 211? 211 divided by 118. Oh, of course, it goes there just once. 118. And the remainder is 93. What about 93 into 118? 93 goes there many times. 118 divided by 93. Again, it will just be once. Just be once. and the remainder will be 25. Then 25 into 93, and 3 divided by 25 with 3 times. To be 3 times. And so what is the remainder? The remainder is 18. And then 18 into 25, that will be ones. The remainder is 7, 7. And then 7 into 18 will be twice. The remainder will be 4. 4 into 7 will be ones. And then 3. 3 into 4, ones. Then 1. This is the GCD. Of course, we had said it, the number we are choosing was relatively prime. Now, so to find the inverse again, we just reversing and using the extended Euclidean algorithm. So using extended Euclid's algorithm, we find the, now, so I done that. You just use that. When I did, I found the inverse to be 1980. I found it to be 1980. So after finding the inverse of 1980, is this inverse that you multiply by x to give you U2. So x, you knew what it is because it's you want to prove. X was 301. X was 301. So take 301 and multiply by 1980, and our mode is still the same. Our mode was 7081. 7081. So what do we get when we multiply these two? When we multiply these two, 301 times 1980, and then divided by 7081, goes the 84 times. 84 times, yes, I mean, it went there 84 times, yes, 84 times. The remainder is 1176. So this is your U2. After finding U2, now square U1 and U2 and call their squares x1 and x2 respectively. So what is x1? X1 is the square of U1, and U1 was 211. Yes, it was 211. 211 mod 7081. 211 times 211 is 44,521. So when you divide it by 7081, goes there 6 times, the remainder is 2035. This is your x1. What about x2? The square of U2 mod 7081. So 1176 times 1176. The answer you get divided by 7081 goes there 195 times, 195 times, and the remainder is 2181. So those, you send those ones as proof that you know x2. So Alex now verifies. Alex verifies that in fact, what you are doing is correct. He multiplies x1 times x2, and that is 2035 times 2181, and is doing this mod 7081. I think it was 7081. Yes, it was 7081. So when he multiplies, let's just multiply that times 2035 divided by 7081. It goes there 626 times, 626 times, and the remainder is 5629. He wants to see whether this 5629 he was sent 5629, and he can see he was sent x squared to be that. Now he's surprised. He wants to know whether you can get the square root of x squared. And to do that, he will not ask you to get the square root of this. He asks you to get the square root of the components that give that. So he'll ask, give me the square root of, he will ask you, give me the square root of x1. Then he will ask you, give me the square root of x2. So you just go back. You know what this, you know x1 was a square of 211. So the square root of x1 is just 211. That is the square of this, the square of this. The square of 2035 is 211. Then what about the square of x2? The square of this, no, the square root. The square root of this. The square root of this, of course, is 1176. So he sent those ones to him. He'll again verify whether you've done what you've sent is correct. He'll again verify. He will now take 211 and square it, mod 7081. He wants to see whether it gives him x1. And when he does that, it gives him 2035. Again, he wants to verify whether what you send him as the square root of x2, which is 1176, is indeed the square root. He wants to verify whether it's indeed the square root. When he does that, he multiplies and he gets 2181. He's convinced, therefore, you know what x is. Because nobody else can give him the square root of x1 and give him the square root of x2 if that person did not know what x was. Nobody else can do that. There is somebody here who tries. Example 3, Eve tries to impersonate Cyprian in example 2. So in example 2, Eve met the conversation between Cyprian and Alex along the way. And you know, we are talking about things like Zcash and Bitcoin and so on. So somebody tries to impersonate Cyprian. And then he wants to convince Alex that now he is the Cyprian, so that they can continue with the transaction. Now, so Cyprian now, Alex asks Eve to prove that she knows X. She had seen the communication between Alex and Cyprian. She had seen N. And she had seen X square. But Alex will ask me somewhere to get the square root of X1. So she's prepared for 1. She's prepared for X1. So if she is prepared to answer X1, she just answer X1, the square root of X1. She cannot answer the square root of X2. But if she prepares herself to answer for X2, then she cannot answer for X1. She cannot answer both. She can only answer one. Now, the first thing she's supposed to convince Alex is that she knows she can find this 56. Because of course, that is what Cyprian did initially. That's what Cyprian did. The first thing Cyprian did was to convince Alex that he can get 56. Because when he sent Alex X1 and X2, when he sent Alex X1 and X2, these ones, Alex was able to get their products. And when Alex got their product, he found it was giving him X2. No, the square of the square, no, not X squared. So that is the first thing Cyprian did. He showed Alex that he knows he can use some steps and give him the X square. Then using those steps, now Alex wants to verify whether he can get the square root of X1 and the square root of X2. If he can get the square root of X1 and X2, it means he can get the square root of this number. That's what just Alex wants to confirm. And of course, I repeat, Cyprian began by showing Alex that using some moves, he can tell Alex how to arrive at X2. Then using those same moves, Alex is supposed to confirm whether using those moves, you can get the square root of X1 and the square root of X2. So if you can get the square root of X1 and X2, it means you can get the square root of X squared. That's what Alex and Cyprian did. So Eve will also come with that notion. She knows the first thing she's supposed to convince Alex is that she can make some moves and arrive at X2. So using those moves, Alex is supposed to find out whether she can get the square root of X1. So she decides on her moves. She doesn't know X. What she knows is X squared. So she'll choose any number relatively prime to N. She's trying to impersonate. So she takes a number relatively prime to N and squares it. This is what she gets. After squaring this number, she gets the inverse of the square. The inverse of the square. That's what she gets using the extended Euclidean algorithm. After getting this inverse, she multiplies this inverse by U square, which she has from the public domain. From the conversation between Cyprian and Alex, she was able to get that X square. So she multiplies this inverse by X square. And that gives her X2 square. X2 square. So this is why she's multiplying mod 7081, and she gets X2 square as 145. So you know, now when she multiplies these two numbers, U2, her U2 square and her U1 square, when she multiplies, these two will give her X square. So she sends those two to Alex. So she calls this one, this square of u1, this square of u1, where was it? This one, 576. She calls it x1. And this square of u2, which is 145, she calls it x2. And as usual, x1 and x2, their product is x squared. So Alex confirms x1 and x2 multiplies mod 7081, and he finds indeed it gives him x squared. So up to there, she has scored. Up to there, she has scored something, because Alex is now getting convinced along the way, but he has to continue with the verification process to the end. He has just confirmed that x squared, x1 and x2 gives him this. Now he asked her, give me the square root of x1. Give me the square root of x1. And she comes back to her calculation. X1 was a square of u1. X1 was a square of u1. So what is u1? Her u1 is 170. So she sends Alex 170. Alex squares it. Squares 170 to see whether indeed it gives x1. X1, what is x1? X1 is just 576. So Alex squares 170. And he finds that it gives him 576. She has again scored. She has scored at that point. Because the 170, the square is 576. So Alex now asks, give me the square root of x2. And she's not able to do that. She's not able to get the square root of x2. That's a very difficult question for her. What she knows is x, the square root of x1, because this is the u1. U1 is the one which was squared to give you x1. So she's able to tell the square root of x1 as 170. But when it comes to x2, x2, it was the square of u2. But what is u2? She doesn't know u2. She doesn't know u2. What she knows is the square of u2. The square of u2 is what she knows as 145. She cannot get the square root of 145 mod 7081. This is a very difficult question. She cannot get that square root. But she knows the square. She knows the square of u2. She doesn't know the square root. That's why I said from the beginning, when she's, for anybody who wants to attack or wants to impersonate, anybody who wants to impersonate always has what he thinks will be asked. So you see, if Alex decides to ask for x1, she scores. If he stops there, she will have scored. But if he continues and asks for x2, she will not score. She will fail. And so when she fails, Alex is able to know that this was an imposter. I hope you've seen why she cannot get the square root of x2. Because x2 was the square of u2, but u2, she doesn't know what u2 is. What she knows is the square of u2 as 145. That's all she knows. Because when we calculated, we just calculated for U2 square. We calculated for U2 square, it was 145. She did not calculate for U2. She calculated for the square of U2. For you to calculate for U2, you must be knowing X. She did not know what X was. So that is how the imposter comes in and then fails. Now, how do you confirm that this protocol is zero knowledge? The first way to confirm that it's zero knowledge is that the test must be complete. What we mean by the test must be complete is that the person who claims to know must always pass. The person who claims to know must always pass. You can see example 1 and example 2, when Cyprian claimed to know X, when he was asked for the square root of X1, he passed it. When he was asked to get the square root of X2, he passed it. And so the person who claims to know, the prover must always pass. And the other test that what we look at to confirm that it's zero knowledge is that the test must be sound. What do we mean by the test being sound? What we mean by the test being sound is that if the intruder comes in, the intruder is able to get only half or 50% of the test and fail the other 50%. So that is what we mean by the test being sound. So it's sound if the intruder comes in, he fails 50% and passes 50%. And then the other thing that we need to look at is that the test needs to be zero knowledge. It needs to be zero knowledge. This means that if there was an intruder, the intruder will not learn anything by listening to your conversation. Will not learn anything. The only thing he will know that Cyprian knows the secret, but he will not learn what the secret is. So that's what we look at for a protocol to be zero knowledge. So I think we shall look at other aspects of zero knowledge tomorrow. Thank you.
Thank you. Thank you. Thank you very much. I think now we are moving into cryptography, much in depth. So let us revise. Let us come to the boot camp. And let us also hold each other's hands, especially for the people who are doing Rust. Now we should be able to compute these proofs and verify them, and prove verification as well, programmatically. So see you all tomorrow. Thank you, Dr. Sakwa.
Asante.